Good evening, abstract algebra. So we are going to just take a quick few minutes during our live stream this evening to do some reviewing for our exam number 2 that is coming up as we begin our next week. So we've done some reorganization of our topics recently, and we've sort of settled upon the material of the next exam being roughly as follows. So there's going to be 5 different learning standards that are a part of the exam that's coming up next. And those 5 are the learning standard number 4, which deals with cyclic groups and being able to count the number of elements of a certain order inside of a cyclic group. Standard number 5, which was all about permutations and the symmetric groups on n symbols. Standard 6, which is about isomorphism, how to compare 2 groups that are the same, or to distinguish between 2 groups that are not the same. Standard number 8, which is about the direct products of groups, and standard 11, which takes the direct products of groups and uses it to define the fundamental theorem of finite Abelian groups, which says that any finite Abelian group can be written as a direct product of cyclic groups whose orders are powers of primes. So what I thought I'd do to try and economize the time that we spend together during this live stream is to kind of treat it as a high concept type of problem. What I mean by that is I want to look at one problem, a problem that's just sort of open-ended, find out as much as we can about the algebraic structure of the group U57. So U57 is the multiplicative group of units modulo 57. And the goal is going to be to say as much as we can about the algebraic structure of that group. In particular, can we discover whether or not this group is isomorphic to some direct product of cyclic groups? And if it is, then what direct product do we want there? So I'm going to try to use this question to visit a bunch of different topics and learning standards that we've seen in the course up until this point, and then I think we're probably going to have to come back at the very end and maybe choose a couple of separate problems about isomorphism and about permutation that will let us get a little bit more practice with those topics. But the other 3, the cyclic groups question, the structure theorem, the fundamental theorem, standard 11, and direct products, we'll get a chance to at least look at all 3 of those through the course of what we talk about here in this problem. So how I want to start is let's just think about the group U57 and what it is, if anything, that we're able to know about this group. So the first thing I'm going to do, actually, is I'm going to go into my browser here, open up a Sage cell for computation, and then just for fun, let's take this Sage cell and let's see if we can ask it to do a computation for me. So what I'd like to know is if, so actually here, what I want is a table of the values of I and I only want to see those values of I that are relatively prime to 57. So how do I get Sage to do that? I need an if statement. So table if GCD of I with 57 is equal to 1, then I want I, otherwise I want nothing. And then I want this for I from 1 to 56. And I think I've got an issue here with my parentheses. I don't think it likes that very much either. Well, let's try it. See if I have my syntax right. I actually need a lot more practice with Sage. I'm not doing such a good job here. All right. Let's just do a quick. So, all right, maybe rather than have Sage do this for us, this is a small enough group. Let's just list the numbers out, and I'm going to stop pretending that I know Sage off the top of my head tonight. So U57 is going to consist of all of those numbers that are the natural numbers less than 57 that are relatively prime to 57. So 1, of course, will always be a part of a U group. 2 is relatively prime to 57, but 3 is not. 4 is relatively prime to 57. 5 is. 6 is not because they share a factor of 3. 7. And 8 will be a part of this as well. Just so that we can know that we're getting the right elements in this U group, if I'm going to list them all, let's take a moment and do a prime factorization of the number 57. So 57 is divisible by 3. Whoops. In fact, it's equal to 3 times, let's see, 3 times 20 would give me 60. So this is 3 times 19. And that's a complete prime factorization of 57. So I know now that the primes that I need to make sure that I avoid are 3 and 19. But anything that's not made of 3s and 19s will be relatively prime to 57. So for example, 10, because it's made of 2 and 5, is going to be relatively prime to 57. Ditto with 11, but not 12 because they share the 3. 13. All right, I'm going to just skip ahead to the end here. 56 is going to be the largest such number. Okay. So there's at least a partial list of the elements of U57. And again, because it's a U group, the operation in this group is multiplication mod 57. Multiplication mod 57. Okay. So first of all, right off the bat, what can we know about the group U57? I'm going to kind of keep a running tally of what we learned here as we proceed. So the first thing that we can be absolutely sure of about the group U57 is that because the operation in this group is multiplication mod 57, and multiplication of integers is commutative, right? A times B is equal to B times A, and therefore when we reduce mod 57, multiplication mod 57 is also commutative. And so the group U57 has a commutative operation. Therefore, it's an abelian group. So I would put that first on my list of things that I would want to know about this group if I'm studying it in an open-ended fashion. It's an abelian group. The other thing we can know about it is that it definitely will have, I don't know how many elements yet, but it's definitely going to have less than 57 elements in it. So in particular, it's going to be a finite group as well. Its order is finite, because we know for sure it's going to have less than 57 elements in it. And maybe now is a good time to actually figure out what the order of this group is. And this is a topic that we wrestled with back in standard number 4. So this is a good review for that particular piece. So let's get out a cocktail napkin here, sort of drop it down on the screen, and figure out how do I determine the number of elements in U57. Order of U57. Well, this is really an answer to the question, how many numbers less than 57 are relatively prime to 57? And by definition, the function that answers that is the Euler phi function. By definition, this is the Euler phi function of 57. So this is the first place where we're seeing the Euler phi function come in handy. It's going to tell me the order of this U group. Now, how do I compute phi of 57? This is where our prime factorization comes in handy. 57 is 3 times 19. And because 3 and 19 are relatively prime to one another, the Euler phi function breaks apart across that multiplication. Right? Because 3 and 19 are relatively prime, we can split apart the Euler phi function in this fashion. So 3 and 19 relatively prime, and that's why I can do this. And then we can compute each of those. Phi of 3 is going to be, because 3 is a prime, right? 3 to the 1 minus 1 times 3 minus 1. And phi of 19 is going to be 19 to the 1 minus 1 times 19 minus 1. I compute those out. 3 minus 1 is going to give me 2. 19 minus 1 is going to give me 18. And so the order of this group is 36. So we didn't list all the elements of U57 up here at the top of the screen, but if we had listed all those elements, there would have been a total of 36 of them. Let's put that in our list of things that we now know about this group. It has phi of 57 equals 36 elements. There we go. So now actually we know one more piece of information about this group. It's a finite abelian group, and its order is 36. So that was something that we would have wanted to have been able to determine back in standard number 4, right? How many elements are there in this U group? There's 36. Okay, let's dwell in chapter 4 for just a little bit longer. and ask the question that I have listed on my agenda here underneath me, which is this group a cyclic group? How could I tell whether or not U57 is cyclic? Is U57 cyclic? Well, in order to figure this out, what I might do is I might just take some of these elements and just see if I can figure out what their order is. To do that, this time I actually am going to use Sage. I think I should be able to do it this one. So what I want to do is I just want to take a number like 2. Let me take the element 2 in this group. And I'm just going to use Sage as a shortcut to compute the various powers of 2. 2 to the 1, 2 to the 2, 2 to the 3. Again, all of those understood mod 57. So let's see if I can get this one right, at least. So for example, what is 2 squared mod 57? Well, 2 squared is going to be 4. 4 mod 57 is going to give me 4, so at least that syntax there is working. Whoa, what just happened? I'm in the wrong browser window here. I'm just trying to get a larger... Just trying to zoom this in a little bit here. Apologies for... Oh, there we go. Now we've got it. All right, so now we can see this a little bit better. So 2 squared mod 57, that's just 4. All right, so let's see if we can get Sage to do a whole list of these. So table of 2 to the k mod 57. And I want to list these. The kth power, 2 to the k mod 57, for k in, let's say, 0 to 56. So I want the first 56 powers of 2 taken mod 57. And again, I'm screwing up my syntax. I think what I need here is one more pair of brackets. Yes, here we go. Perfect. So now what we're looking at here in this table, as it scrolls down above my head here, is on the left-hand column I have here the power of 2 that I'm talking about, and on the right-hand column we have 2 raised to that power mod 57. So for example, 2 to the 4th mod 57 is 16, 2 to the 5th mod 57 is 32, and so on and so on and so on. And what we find out is that by the time we get down to, the 18th power of 2, the 18th power of 2 mod 57 has come back around to 1, which, remember, 1 will then be the identity element of U57. Because after all, the operation in U57 is multiplication. 1 is our multiplicative identity. And so that means that 2 to the 18th power gives me the identity element. But there's no smaller power of 2, other than the 0th power, of course, that does so. So this little calculation shows me that the order of the number 2, the element 2 in U57, is actually 18. So let's think for just a second about what that has told me about the element 2. It tells me that the element 2 has order 18 in my group, right? Because the 18th power comes back around to the identity. The identity is our unique element of order 1. But no smaller power than the 18th power of 2 gets me back around to that identity. What's nice about this Sage code now is that I can use it to check the orders of some other elements as well. Let's check the order of the element 4. But even before I check the order of the element 4, I know for sure what that element's order is going to be, because 4 is just 2 squared. And so because 4 is 2 squared, that means that 4 is going to come back around to the identity in half as many steps as 2 did. And so we would expect that the order of 4 is going to be half the order of 2. We expect the order of 4 is going to be 9. Let's check it. So when Sage lists out all of my powers of 4, sure enough, the first power of 4 that comes back around to the identity is the 9th power. So the order of 4 is 9. Let's check 5, and then maybe we can move on after checking a few orders. How about 5? What does it generate? So what we're actually looking at, or what we're having Sage look at here, is it's giving us the full list here of the elements that 5 can generate as a cyclic subgroup of U57. So those elements are, for 5, 1, 5, 25, 11, 55, 47, and so on and so on and so on. But 5, just like 2, comes back around to the identity after 18 powers. So the order of 5 is 18. We're reviewing for an exam this evening, and so you might see me using Sage and ask to yourself, well, I mean, how would we do this if we didn't have technology in front of us? And so I wouldn't expect you to do something this laboriously computational as part of an exam. That's why what we're going to do next, now that we've done a few computations, what I want to do next is move ahead and see if we can be more sophisticated about saying something about U57 that will illuminate its algebraic structure. So far, we have not been successful in finding any generator that will generate the whole group. We've managed to find an element of order 18. We've managed to find an element of order 9. But if I were looking for a generator, I would need for that generator to have an order that's equal to the order of the whole group. Right? If U57 were cyclic, it would have to have an element whose order is the same as the order of the group, which would be 36. So the question I'm really kind of asking myself here is there an element of order 36? That such an element, if it existed, would be a generator for this group, and therefore the group would be cyclic. If yes, then the group is cyclic. Let's take a brief moment, and just before we go forward and get sophisticated about it, let's have one more opportunity to flex our Euler phi muscles a little bit. If this group had an element of order 36 in it, and therefore the group would be cyclic, let's just pause and ask how many such elements would there be? There'd be a total of phi of 36 such elements. Right? And again, this is an opportunity for us to evaluate phi of 36. So split 36 into a prime power factorization. That would be 4 times 9. 4 times 5, 9. 4 and 9 are each prime powers, and so this gives me a prime power factorization, and 4 and 9 are relatively prime, so we can use this same argument as we did over here to use the multiplicative property of the Euler phi function to make it phi of 4 times phi of 9, as I've done here. And then this is going to be 2 to the 2 minus 1 times 2 minus 1 times 3 to the 2 minus 1 times 3 minus 1. Phi of 4 ends up being 2. Phi of 9 ends up being 3 times 6. And so there would be 12. So if this group were cyclic, there would have to be 12 different members of this group, each of which is capable of generating the whole group. Right? There have to be 12 generators for a cyclic group of order 36. But there's 36 elements in this group in total. We've ruled out only 4 of them as far as determining whether they're generators or not. Maybe before we go forward, let's check 7. I mean, we've got the Sage code right in front of us here. Oh, 7 is already wrecked, right? 7 comes back around to the identity after only 3 powers. So we're not doing so hot in our search for a generator for this group. And so this might be the point at which we take a step back and say, well, I'm going to start doubting that this is a cyclic group. But if it's not a cyclic group, then what is it? That's the question that we want to use the fundamental theorem of finite abelian groups to help us to illuminate. So let's take that step forward into learning standard number 11. And the question that we're going to try and address here is as follows. So the question that I want to tackle now is, given that U57 is a finite abelian group of order 36. It is abelian, and its order is 36. Then the question I'm asking here is, what does the fundamental theorem of finite abelian groups tell me about the structure that this group may have? What structures, parentheses, are possible? And when I say what structures are possible, what I'm really asking here, adjust my camera real quick. I keep getting these little triangles. What I'm really asking is, what direct product of groups that we understand really well, might U57 be isomorphic to? So we're going to use the fundamental theorem to help us illuminate this question. So, what is a fundamental theorem going to tell me? Fundamental theorem, first of all, may be applied precisely because this group is a finite abelian group. And the fundamental theorem is exactly a theorem that classifies the possible structures of finite abelian groups. If our group were infinite, the fundamental theorem would have nothing to say. If our group were not abelian, the fundamental theorem would have nothing to say. But because it's both finite and abelian, we can apply this theorem. So let's do it. What would it look like? Well, the first thing we would need to know is what are the different possibilities of prime powers that multiply together to give me 36? So 36, again, as we said in the previous slide here, we could get a prime factorization of this as 4 times 9, prime power factorization, right? And 4 is 2 powers of 2. And 9, of course, is 2 powers of 3. And so if we're using the metaphor, the chip stacking game metaphor that we've been using in our class to kind of help explain the thought process that goes into the classification that we're about to do, the metaphor here is that my group of order 36 can be structured by stacking 2 red chips and 2 green chips. And so we want to figure out what are the different ways in which I could do that. So let's get my chips out here. Get my chips on the table. So 2 red chips and 2 green chips is what I have to work with. Each of those red chips is going to represent an order 2 factor. Each of those green chips is going to represent an order 3 factor. So one option that I have for stacking these chips in my stack it chip game metaphor is just to stack all 4 of these chips on top of each other. So 2 red chips on top of each other and 2 green chips on top of each other. And in that particular chip stacking arrangement, since each of those chips represents an order 2 and order 3 factor and they're all stacked together, I would just multiply those all together and find out that the group that we'd be talking about here, 2 times 2 times 3 times 3, that would be Z36. Right? And so there is one option for what the algebraic structure of this group might be. Right? So this is option number 1. And to find the other options, what I want is I want to try and rearrange these chips in ways that I know are going to give me a distinct group to Z36. So any move which is legal in terms of our stack it rules of the game is not going to give me a different group. It's going to give me the same group up to isomorphism. Right? So for example, if I were to take both of these green chips and unstack them from the red chips, I would get what looks like a different group. But because that's a legal stack it move, I know that that group is going to be isomorphic to the group that we started with here, right? And so just by unstacking those chips, get my big head out of the way here, just by unstacking these chips, I haven't actually gotten myself a new group because I've just followed the rules of the stack it game. But when I unstack them like this, the group that I have now is Z4 direct product Z9. So those groups are isomorphic. So I haven't gotten something different by using a legal stack it move. Let's take a moment and step back one more time. So we're stepping back from a step back now and ask how many possibilities, how many distinct groups up to isomorphism can I have? How many distinct options? And remember, if I want a distinct group, then I need to apply one of these illegal moves from stack it. And the illegal moves are moves that only serve to separate stacks of the same color or to merge together 2 non-empty stacks of the same color, right? And so it turns out that the formula that counts the number of distinct options for which to do so was this product of partition functions that we talked about in class last week. So the number of distinct options will be the product of the partition functions of the number of each chip that I have. So the answer to how many distinct options is it's going to be the partition function of 2 being the number of red chips that I have here, multiplied by the partition function of 2, which is the number of green chips that I have to play around with. So again, those 2's, just to make sure that we're clear, are both coming from the number of chips of each color that I have, which are coming from the exponents in the prime factorization. Number theorists call these the valuations. It's the 2-adic valuation and the 3-adic valuation, respectively, are 2 and 2. And the partition function of 2 is just how many different ways are there to express 2 as a sum of non-negative integers. And there's 2 ways to do it. We can write it as a 2, or we can write it as a 1 plus 1. In other words, we can have the 2 chips of a given color stacked, or we can have them unstacked. And those are the 2 options for each. And so this partition function is just 2 times 2, that's 4. So I know now that there are going to be 4 different options for what the structure of this finite abelian group of order 36 is going to be. I like doing that step up front because that way I know if I need to keep looking, or as soon as I've found 4 distinct options, I know I can stop looking. Right? So now I know there's going to be 4 options for me to look at. So now it just remains to try and figure out what those other 4 options are. So to get from an option to a different option, I have to do an illegal move for my stack it game. In other words, one that only separates chips of the same color or merges together non-empty stacks of chips of the same color. So let's say I start from this unstacked Z4 direct product Z9. One illegal move that I could do is just to separate these 2 red chips from one another, so that instead of being stacked, my red chips are unstacked. So what I'll have then is red chips sitting next to each other like that, and then a stack of green chips that are together. And in the metaphor of the game, that's going to correspond to the direct product Z2, Z2, Z9. But of course, if I wanted a simpler way of understanding what this group was, I could try and make as big of a stack as I can to give me as few factors in my direct product as possible. And the way to do that with a legal stack it move, remember, would be to take one of these red chips, stack it on top of the green chips, and give me, again, because that's a legal move in stack it, it gives me an isomorphic group to the one that we had there. One in which we have my green chips still stacked, but now I'm stacking a red chip with them, and then I have one red chip that is off on its own. And so that's the group Z2, direct product Z18. Okay. And so that is a distinct option from this one, because there's no legal stack it move that can get me from one of these positions to one of those positions. What's a third option? Well, let's go back to Z4 plus Z9 down here. A third option would be to unstack the green chips instead of unstacking the red chips. So keep the red chips stacked together, but separate the greens from each other. That's an illegal stack it move, and so it gives me a distinct group up to isomorphism. And in our metaphor, it's going to correspond to the direct product Z4, direct product Z3, direct product Z3. And if I want to have as few factors in my direct product as possible, I'll restack these together. Stack one of the greens with the reds. And then that will give me a slightly simpler expression of the same up to isomorphism finite abelian group. So I have one green chip that's off on its own. And the slightly simpler expression would then be Z 2 times 2 times 3, right? 2, 2, 3. That's going to be 12. Direct product Z3. And so that is a different group than that, which is a different group than that, up to isomorphism, right? And then finally, my fourth option would be to do both of the unstacking maneuvers, right? Take all of my chips and separate them into 4 separate stacks. So the green chips get separated, and the red chips get separated. Let's get that position listed here. And if all of those get separated, then I can express this group as a direct product of 4 factors: Z2 direct product Z2, direct product Z3, direct product Z3. But I can also try and express this as simply as possible by doing the only legal stack it moves that I have here, which is to stack a green chip with a red chip and the other green chip with the other red chip. And so the simplified version of this position would have the 2 red chips in separate stacks and the 2 green chips combined with them in separate stacks. And as you can see, what's going to happen there, each of these chips is going to have each of these stacks is a 2 and a 3, representing the cyclic group Z6. And so I have Z6 direct product Z6. And now that I did the partition function thing to count the total number of options that I have, now I know that I'm done. I don't have to keep looking for more versions of finite abelian groups of order 36. We have 4 distinct options, and therefore we have a complete list. Okay? There's no possible way to get another finite abelian group of this order. So, what now are we going to be able to conclude based on the information that's here? We know for sure, and this is the power of the fundamental theorem. I think I've kind of undersold this in class. But now that we have the complete list down here on my screen, the fundamental theorem says that U57, because it is a finite abelian group of order 36, it must be isomorphic to one of these 4 groups. U57 must be isomorphic to one of these options. And that is a really powerful thing for a group theorist to be able to say, right? There's infinitely many different finite groups out there in the world that we could worry about. Even just knowing the order of a group. If I know that my group has order 36, there's actually, dozens of different groups of order 36 out there. Some of them, most of them, are not abelian. But of those that are, the fundamental theorem says, up to isomorphism, there's only 4 possibilities. And so if U57 is abelian and has order 36, it's got to be isomorphic to either option 1, option 2, option 3, or option 4. So, of course, now our question is, how do we know which one it is? How do I know which of these options U57 is isomorphic to? To begin to answer that, I actually want to go back to the previous slide of information that we figured out about U57. One of the things we learned about it is that it has an element of order 18, and it has an element of order 9. Let's see if we can use that information to rule out some of the possibilities that are over here. So real quickly, I just want to add that into the list of things that I know before we go any further than what we had. Whoops, sorry. Let's add that into my list. So I know that the group has elements of order 3, 9, and 18. Right? Just the computations that we did in Sage were enough to convince us of that fact, right? We know it has elements of those orders. We weren't able to find an element of order 36, but we were able to find elements of orders 3, 9, and 18. And of course 1. I guess I'll list it, even though every group ever in the universe, because of the identity property, has an element of order 1. Okay, so armed with that information, what we can do is go back to our list of these 4 groups and ask which of these 4 groups has an element of order 18. Which option or options has elements of order 18? And so this question now becomes a combination of the skills that we built in Chapter 4, where we asked the question about cyclic groups that said, does a cyclic group have an element of a given order that is a divisor of the order of the group? And remember, for cyclic groups, the answer is always yes, right? Every cyclic group has elements of every single order that divide the order of the group, which is why we love cyclic groups, why we understand them so well. They have elements of all those orders that we could ever want them to have. But of course, if my group is not cyclic, I can't guarantee that that's true. Right? Not every one of these groups probably will have an element of order 18. Just because 18 divides the order of the group does not guarantee that there exists an element of that order unless that group happens to be cyclic. So let's start searching I'm going to clear out some space here. And now we can start looking and asking, how are we going to be able to tell which of these groups, options 1, 2, 3, or 4, will have an element of order 18, rather. Well, let's start with option 1. Option 1 is the only one of these options which is a cyclic group, right? It's a cyclic group of order 36. It's got a generator that we can call upon. And so since this is a cyclic group, we know from the basic tenets of chapter 4, right, that it must have an element of order 18. An element of order 18. Right? In fact, why don't I, just to make my life a little bit easier, let's make this into a little table. Does there exist, question mark, an element of order 18? And in the case of our cyclic group, the answer is yes. Because after all, 18 is a divisor of 36. And cyclic groups have elements of every divisor of the order of that group. Right? So yes, there's absolutely an element of order 18 in that group because this group is cyclic and 18 divides 36. Let's move over to option 2. And the best way to understand these groups is going to be this most simplest, the fewest number of factors in its expression. Z2 direct product Z18. Will this group have an element of order 18? Keeping in mind that how we find the orders of elements in a direct product, and this is the key ingredient in chapter 8, is to use the least common multiple of the orders of the elements in each of the factors. So the LCM theorem is our main ingredient here. It's our secret weapon. The LCM theorem is actually the entire reason that the stack it game that we've been playing with chip stacking over here gives us the metaphor that we need to understand the classification of finite abelian groups. And so the LCM theorem is going to say there exists an element of order 18 if it's possible for me to find elements in these two factors, Z2 and Z18, whose orders have a least common multiple equal to 18. Can I do that? Can I find a divisor of 2? Because after all, since Z2 is cyclic, it's going to have elements of every divisor order that divides 2. And Z18 is going to have elements whose orders are realizing every divisor of the number 18. And so if I can find a divisor of 2 and a divisor of 18, divisors of 2 and divisors of 18, whose least common multiple is equal to 18, then the answer to this will be yes also. And sure enough, the easiest way to do that is just to take an element of order 18 in Z18. So the divisor that I'll choose for my Z18 here is 1. Sorry, not 1, 18. And then I would just take, let's say, the element of order, I could take either, really, the element of order 1 or of order 2 over here. Both of them are going to have least common multiple of 18 when I combine them with 18. So I'll just take 1. And so sure enough, we find out that the answer to this is yes. Right? There is an element of order 18 in this group. And if we want to be really explicit about what that element is, we can do so. So I just need an element of order 1 from Z mod 2. And there's only one element of order 1 in any group. It's the identity element. So let's take the identity element from Z mod 2, call it 0, remember. 0. And I take an element of order 18 from Z18. In other words, a generator of Z18. So let's just take 1. That's an element of order 18 in Z18. And if I just put them together into an ordered pair, 0, 1 is an element of order 18 in the group which is isomorphic to Z2 plus Z18. So this group has an element of order 18. This group has an element of order 18. Let's keep going. What about option 3? Will there be an element of order 18? Well, the answer here again is going to be yes. Because if I can find a divisor of 12 and a divisor of 3 whose least common multiple is 18, then because each of those factors is a cyclic factor, we will get elements of that order. So how do I get a divisor of 12 and a divisor of 3 to have a least common multiple of 18? I'll just take, I'll just take 3 as my divisor of 3 that I'm using over here on this side. And then 3 least common multiple with what is going to give me 18? 3 least common multiple, well, is this going to work? Because if I do 12 with 3, the least common multiple is going to be 12. If I do 6 with 3, the least common multiple is 6. So 3 is a divisor of 12, after all. And so any divisor of 12, when I pair it with 3 in a least common multiple, I'm never going to get anything larger than 12 in this LCM. And if I take any other divisor of 3, the only other divisor of 3 I have to work with is 1. But I can't get another element of a big enough order on this other side to give me a least common multiple of 18. And so there is no way to get 18 as a least common multiple of a divisor of 12 with a divisor of 3. And so remember, because it's an if and only if statement, that if k is a divisor of n, then there exists an element of order k in the cyclic group of order n. Because that's if and only if, that means that there does not exist an element of order 18 in this group. So option 3 is not going to work. And for the very same reason, we can demonstrate that option 4 is not going to work either. Right? Because there's no divisor of 6 that if I take the least common multiple of that divisor with 6 with some other divisor of 6, that least common multiple is going to end up being 18. So what we're doing here is we're trying to narrow down the universe of possibilities, right? How can I figure out whether or not my group U57 is isomorphic to one of these 4 options? We know it's isomorphic to one of these 4 options, and so we start looking for disagreements. We start looking for reasons to disbelieve that it's isomorphic to one of these or the other. And since we directly computed that the group U57 had an element of order 18, we can go through and rule out option 3 and option 4, because these finite abelian groups do not have elements of order 18 in them. Option 1 and option 2, on the other hand, do have elements of order 18. So we're getting warmer. We found one more thing out in our little detective piece over here. Right, so let's write that down into our list of things that we now know about this group. So the fundamental theorem says that this group is isomorphic to one of the following. And I'll just write all 4 of the options that we had. So Z36 or Z2 direct product Z18 or Z12 direct product Z3, or the last option was Z6 direct product Z6. Right, so the fundamental theorem was our key ingredient here, right? It narrowed down our universe of possibilities to say that one of these 4 options had to be the one. Let me create some spacing there just so that's easier to read. Whoops. Copy that, paste, compile. There we go. So the fundamental theorem says that these are the 4 possibilities. But since the only 2 of these possibilities had an element of order 18, since we know that U57 has an element of order 18, there are now only 2 possibilities. Z36 or Z2 plus Z18. Okay. So we're converging on an answer here. Let me combine this into one space. So it is a finite abelian group. And the group has 36 elements. We found out by computing that the group has elements of order 1, 3, 9, and 18. The fundamental theorem told me that there are 4 possibilities, but having an element of order 18 means that there's really only 2 possibilities, Z36 or Z2 plus Z18. So we're down to the wire. We have to make a call. We could flip a coin. I don't particularly feel like flipping a coin on this. So let's think if there's anything else that we could do to try and distinguish between these 2 groups, Z36 and Z2 direct product Z18. And so for that, again, I'm going to go back to our universe of possibilities here. Let's sort of gray out the ones that we know are not going to work anymore. So option 3 is off the table. Option 4 is off the table. Right? So those we know for sure are not going to work. So let's ask the question, how could we tell the difference between Z36 and Z2 direct product Z18? What are the disagreements we can find between those two groups? The most obvious one is the fact that the former option, option 1, is a cyclic group, and option 2 is not a cyclic group. So one important distinction is that Z36 has an element of order 36. Has an element of order 36. And Z2 direct product Z18 does not. So I want to ask the question, are there any other element orders that distinguish between these two groups? And so this is, again, going to be an opportunity for us to think about the LCM theorem, right? The theorem that tells me that in a direct product of two groups, the order of an element is the least common multiple of the orders of the elements that are taken from each of those factors to make the ordered pair. Right? So let's try and get a complete list here of the orders of elements that exist in both of these groups. Because if we can find another potential disagreement other than an element of order 36, maybe that other disagreement will be easier to look for than the ones that we've been doing so far. Right. So, looks like I'm having a little bit of a issue here. Let me just get a blank screen. So I want to think about both of my groups, Z36 and Z2 direct product Z18. And I want to have a list of what element orders exist in these two groups, Z2 direct product Z18. Whoops. Sorry, I'm writing off the screen a little bit here. Let me just nudge it down. There we go. So what element orders do we realize in these two groups? Orders present. Well, of course, both of my groups are going to have elements of order 1, actually a single element of order 1, because that's the identity element, the unique identity element. Right? Meanwhile, Z36, because it's cyclic, has an element of order 36. Right? It's the generator, or a generator, of the entire group. Right? And because Z36 is cyclic, remember, cyclic groups are the best groups in the universe, because everything we want to be true about them that's not true in general for all groups ends up usually being true for cyclic groups. And one of the most important such things is that every divisor of 36 will have an element of that order in my group. So 1, 2, 3, 4, 6, 9, 12, 18, and 36. I think those are all the divisors of 36. Let me just double check. Well, let's think about it. So 36 is 2 squared times 3 squared. So I have 3 choices for an exponent on the 2, 0, 1, or 2. I have 3 choices for the exponent on the 3, 0, 1, or 2. So there's 9 choices for how to arrange the exponents in a divisor of 36. And there are 9 divisors that I've just listed here. So those are all of them. Okay. So there's all the orders that are present in the group Z36. Let's do the same thing for Z2 direct product Z18. Now, we already convinced ourselves that there is no element of order 36. But we also convinced ourselves that there was an element of order 18. Let's think about the other possibilities. What about an element of order 12? An element of order 12 I would have to get by taking a least common multiple of a divisor of 2 with a divisor of 18, and that least common multiple will have to give me 12. Well, I don't think that's going to be possible, right? How can I have 12 be the least common multiple of a couple of things? Well, the only divisors I could pick here for this 2 are 1 or 2. And the only way to get 12 as the least common multiple of 1 with something is to have a 12 here. But 12 isn't a divisor of 18, so that's not going to work. So then the only other way to do it would be to put a 2 here. The problem is that 2 is already a divisor of 12. So the only way to get a least common multiple of 2 with something to equal 12 would be to have a 12 here. And that's not going to work again because 12 isn't a divisor of 18. So there is no element of this direct product group that has order 12. Remember, one of the ways that we saw this using the stack it game metaphor was to think about what is the number 12 actually represented by in stack it. It's 2 red chips and a green chip, all part of the same stack. Right? And that 2 red and a green is part of the same stack here in this group, but there's no arrangement of this direct product of groups that has 2 reds and a green in the same stack. So 12 is not a possible element order for Z2 direct product Z18. What about 9? Let's go back to the chips again. 9 is 2 red chips stacked on top of one another. 2 green chips, because the greens are my 3s, right? And so this Z36 has an element of order 9. There's my 2 green chips. But so too does this group. Here's my 2 green chips sitting right here. So this factor Z18 has an element of order 9 in it. And therefore, if I just take that element of order 9 paired with, let's say, the identity element over here, I'm going to get an element whose order is 9 in that direct product. So yes, there will be an element of order 9 arising as the LCM of 1 and 9. Right? Okay, so we do have an element of order 9. Order 6, do I have a red and a green chip stacked together? I do, right? There's an element of order 6 here in Z18. And so we can get 6 as an LCM of 1 and 6. Or, equally well, it could be the LCM of 2 and 6. That's totally fine. How about 4? Well, 4 is what I would get here by stacking 2 red chips into the same stack, which I have in option 1, but in option 2, I don't. There's no arrangement, no legal stack it arrangement of these positions that's going to give me 2 red chips stacked together. And for that reason, there is no element of order 4 in this direct product. And finally, we'll go back a little further. Order 3, order 2. Can I get each of those? I sure can, right? Because 3 is a prime, 2 is a prime. I can find a stack that has 1 green chip for 3. I can find a stack that has 1 red chip for 2. And so, yes, I definitely get these arising as the order of elements in this direct product. For example, the LCM of 1 and 2, and the LCM of 1 and 3. All right, so if there are going to be disagreements that we could exploit to determine whether or not, determine which of these 2 options my group falls into, I could try and rule out the possibility of whether or not my group is cyclic and so has an element of order 36. Or I could also go looking for elements of order 12 and see if they're there, or go looking for elements of order 4 and see if they're there. Right? If I find even one element of order 4 in U57, then I know for sure that U57 will be isomorphic to Z36. If I find even one element of order 12, I know that my group will be isomorphic to Z36. So the only way to prove that it's isomorphic to this one is to prove that there are no such elements of order 4, 12, or 36. That seems like more of a challenging thing to do, but at this point I think we just start being computational with it. Let's real quickly go down the list here, just again for one more exercise in how many elements of each of these orders would have to exist in Z36, because this could also help us to do some ruling out. Remember, these are each going to be equal to phi of k for k equal to each of these divisors of 36. So phi of 1 is going to be 1. Phi of 2 is also 1. So there's one element of order 2. There will be phi of 3, which is 2 elements of order 3. Phi of 4 is 2 elements of order 4. Phi of 6 is going to be 2 elements of order 6. Phi of 9 is 6 elements of order 9. Phi of 12, 12 is 3 times 4, so it's going to be 2 times 2 is 4 elements of order 12. Order 18, 18 is going to be 2 times 9, and so this is going to be 6 elements of order 18. And then as we said before, 36 is 12. And let's quickly add these up. 12 and 6 is 18, and 4 is 22, 28, 30, 32, 34, 35, 36. So we've accounted for all of the elements in Z36. There's going to be this many elements of each of these orders. Let's see if we can do the same thing over on this side. So this gets a little bit more interesting, because there's a little bit more combinatorics going on here. The number of elements of order 1 is still 1, for sure, because there's a unique identity element in this group. But what about elements of order 2? How many elements of order 2 can there be in Z2 direct product Z18? This is going to be the same as the number of ways to create 2 is the least common multiple of two things. But there's two ways to do that, isn't there? I could take the least common multiple of an order 1 element from here and an order 2 element from there, or I could choose the order 2 element from the first factor and an order 1 element from the second factor. Or I could choose an order 2 element from both factors. Right? Here are the three different ways I can get 2 as a least common multiple of a divisor of 2 with a divisor of 18. There's 3 ways to do it. And that is also a disagreement between these two groups. Both groups have elements of order 2, but Z36, the cyclic group, only has 1 element of order 2. This group has 3 different elements of order 2. And so if we wanted to, we could use that as a way to try to distinguish between these two groups. If I'm looking through U57 and I can find more than 1 element of order 2, then I know for sure that my U57 must be isomorphic to Z2, direct product Z18. All right, I think it's probably time to punt and do some more calculation with Sage. Let's go through and use, there's actually a, let me look up the name of the Sage function, but there's a great Sage function, Sage math, multiplicative order, yeah, that's what it's called. All right, so there is a handy-dandy multiplicative order function in Sage. Yes. It is called literally multiplicative underscore order. So let me show you how it works. This can be something helpful for your poking around if you're working on this at home. Obviously, you wouldn't do this on an exam. So let's suppose that I wanted to know whether or not my group, U57, has an element of order 2. What I can do is I can just have Sage list all of the orders of the elements in U57. So for each value of k, I'm going to have mod of k57 dot multiplicative underscore order, parentheses, for k in 1 to 56. So Sage is going to make a table of the multiplicative orders. Uh-oh, what doesn't it like here? I think I just have, yeah, I need one more square bracket right there. There we go. Uh-oh, still doesn't like it. Right, multiplicative order of 3 is not defined since it's not a unit modulo 37. All right, so for k in 1 dot dot 56, do, and then on the next line here, what I want to do is just print k, and then mod k57 multiplicative order, but I only want to do that if the GCD of k with 57 is equal to 1. Then print this. Whoops. I'm screwing stuff up here. I'm thinking that my Sage syntax is not availing me here. Give me a quick second. I'm going to go look up how to do that one more time. Okay, that is probably what I want. So let's try this again. K, comma, mod k57 dot multiplicative order. Sorry, I'm doing Sage that you can't see for a moment. For k in 1 to 56, if GCD of k with 57 is equal to 1. I'm going to cross my fingers and evaluate this one. Nope, it definitely did not like that. Maybe if I put those around it. Now we got it. There we go. So this doesn't look pretty, but I'm going to put it back up on the screen here for you. So what I've done here is I've told Sage to print out each value of k along with its multiplicative order mod 57. So I'm literally asking what is the order of this element in the group U57 for each k from 1 to 56, provided that k is relatively prime to 57, right? And we have to know that it's actually an element of the group U57. And so the list that's behind my head right here, that's listing the orders of every single element of U57. And sure enough, if I count these up, I find that there are, how many elements of order 2 do I see? And I'm thinking that I must have done my calculation incorrect up there before, because here I'm finding one element of order 2. 56 is an element of order 2, right over my shoulder right there. 37 is also an element of order 2 in U57. Oh, and here 20 is an element of order 2. So there's 3 elements of order 2, just as we claimed a minute ago. There's a bunch of elements of order 18, but there is no element of order 12, and there is no element of order 4 that I see in this whole list. And notably, there's no element of order 36. So this group is definitely not a cyclic group. So what would be the easiest way to turn up a disagreement here? I think probably the easiest way would be to maybe look for these elements of order 2. These seem to be the easiest things to look for because they don't require taking a lot of powers. So what I might do, if I were really trying to economize, right, is I might look at this list and say, well, elements of order 2 are pretty easy to find. I just have to take the square of each of my numbers, mod 57. If I find more than one element of order 2, then I know for sure that my group must be isomorphic to this option over here. So let's make that our conclusion and wrap things up for this particular example. So last bullet point. Since 20, 37, and 56 are all elements of order 2 in U57, we conclude that U57 cannot be cyclic. And again, if U57 were a cyclic group, let me scroll this up here. If U57 were in fact a cyclic group, then it would only have phi of 2, in other words, 1 element of order 2. But that wasn't the case, right? If it were cyclic, it would have phi 2 equals 1 element of order 2. And therefore, we have identified the algebraic structure of U57. It is isomorphic to Z2 direct product Z18. There it is. That's the end of our little detective mission here, right? So let's go all the way back up to the top of what we learned about this group and just sort of review. So U57, it's the multiplicative group of units mod 57. It's a finite abelian group. It's finite because it definitely has a finite number of elements. It's abelian because multiplication mod 57 is a commutative operation. So it's a finite abelian group. Its order is the Euler phi function of 57, 36, right? And so it's a finite abelian group of order 36. We also directly found out that it had an element of order 18, right? And the fundamental theorem, this is where the fundamental theorem came in, says that U57 has got to be isomorphic to one of the only 4 isomorphism classes of abelian groups of order 36. And those we found by doing the stack it game, right? Z36, the only cyclic version, Z2 direct product Z18, Z12 direct product Z3, and Z6 direct product Z6. We were able to rule out the latter 2 choices because those groups did not have elements of order 18. We knew that again by taking the least common multiples of divisors of each of the orders of those cyclic factors. So that narrowed us down to only the possibility of Z36 and Z12 direct product Z18. And then, if we were to directly compute that there was more than one element of order 2 in this group, and we could do that by finding, for example, that 20 squared, that's 400, which is 1 mod 36, sorry, 1 mod 57, And then 56 squared is whatever 56 squared is. 30,136, but that's also equal to 1 mod 57. That it had more than one. This group had more than one element of order 2. And therefore it cannot have been a cyclic group, because a cyclic group of order 36 will have, a cyclic group of any order that has an element of order 2 will have only one element of order 2 in it. Since there was more than one in this group, our group cannot be cyclic, and so it can't be Z36. It had to be Z2 direct product Z18. Now, if you're really interested to know more about classifying the U-groups, there's a whole set of these 3 U-group structure theorems that we could draw from. We didn't have the time in our semester to go over those theorems, but they're really nice. The tricky part about them is that to prove them really requires you to dive into some number theory. So there's not really an abstract algebra proof that classifies them, but because it's all about divisibility, it has everything to do with number theory and a little bit less to do with abstract algebra. So I want to pause here for just a minute, and then when we come back, I want to do just one more example of a problem that's going to give us a chance to talk again about permutations and talk about isomorphism. So we'll come back in just about half a minute or so and do one last example. So the last thing that I want to do in our review session here is take the opportunity to talk about isomorphism and to talk about permutations. Those are our topics number 5 and 6 for the semester. And I want to do that by smushing the two of them together into one problem. This is a problem that last semester I assigned to students just as part of a homework set. And it was a tricky enough problem that in the class of 20 or 23 or so students, there are really only 1 or 2 students who are able to sort of noodle this out on their own. This is one of those that takes a lot of thinking and a lot of understanding about both isomorphism on the one hand and also the way that permutations work on the other hand to tease out. So here's what the problem looks like. It just simply asks you to prove that, I suppose I need to quantify n here, for n greater than or equal to 3. For n greater than or equal to 3, the alternating group on n symbols is isomorphic to a subgroup of the symmetric group on 2 more symbols, Sn plus 2. So what in the world does that mean? And how are we going to try and tease that out? So real quick, let's just think about what an example of this statement would look like just for a concrete value of n, just so that we can try and get our arms around what this might look like. So let's just take that smallest example. If n is equal to 3, then what are we saying here? We're saying that there's a group A3. This is the group of even permutations of 3 symbols. And there's only 3 of those. 3 factorial over 2. And the 3 permutations here are the identity permutation, the 3 cycle 1, 2, 3, and the 3 cycle 1, 3, 2, which is the inverse of 1, 2, 3. Right, so there are the 3 elements of A3. And then what this theorem is claiming is that there is a subgroup of S5, and now S5 is a gigantic group. I mean, compared to A3, it's a gigantic group, right? It's got a total of 5 factorial, and 5 factorial is 120 elements in it. So there's a whole bunch of elements that we have to choose from here. But one of the things that we notice is that I actually have the statement of this theorem backwards, because the way that this theorem is stated, it is completely and utterly obvious why this thing should be true. Yeah, I have this theorem backwards, I'm sorry. Because it turns out every element of A3 is exactly equal in cycle notation to a corresponding element of S5. because every element of A3 is an element of S3, and every element of S3 can be realized as an element of S5 that happens to be a stabilizer of the 4th and 5th positions. So this is actually not a very interesting theorem as it's written. AN, of course, is isomorphic to a subgroup of Sn plus 2. So really the interesting theorem reverses the roles of S and A here, and that's the one that I really want to look at. I want to prove that Sn is isomorphic to a subgroup of An plus 2. So, all right, let's get this the right way around. I think this is the problem with doing problem-solving sessions this late at night. It's about 10 p.m. here as I'm recording this, so my brain is not firing on all cylinders. It's also the night before Easter, and I have to be up at a sunrise service at my at my church in the morning at about 6 a.m., so I really should be sleeping. Let's try and wrap up this example, but I want to wrap it up by solving the correct exercise here. So S3 has 6 elements, right? It's got the identity, it's got the transpositions 1, 2, 1, 3, 2, 3, and then it has the 3 cycles rather, 1, 2, 3, and 1, 3, 2. Right? So S3 is a group of 6 elements, and then the claim here is that it's isomorphic to a subgroup of A5, and A5 would have 5 factorial over 2. That's going to be 60 elements in it. So it's going to have the identity, it's going to have 1, 2, 3, it's going to have 1, 3, 2, it's going to have 1, 2, 4, it's going to have 1, 4, 2. It's going to have a whole slew of stuff in here. It's going to have the 2 plus 2 cycles, 1, 2, 3, 4, ... It's going to have some 5 cycles. Those are even permutations. 1, 2, 3, 4, 5. There's going to be 24 of those 5 cycles, right? So there's a whole bunch of stuff here. And even if we could list out all 60 elements of A5, it's pretty clear, right, that the identity element of one of these groups is going to correspond to the identity element of the other. But why should that be clear? That should be clear because what we're trying to do is establish an isomorphism. And if we're establishing an isomorphism, then that isomorphism, if I call it phi, has got to send the identity element of one group to the identity element of the other group. That's something that every isomorphism, just because of the homomorphism property, is guaranteed to do. So I know the identity elements of these groups will be related together by whatever isomorphism that we develop. Well, what about some of these other elements? Well, the other thing we know about isomorphism is that it doesn't just preserve the order of the identity element, which is order 1, it would also preserve the order of any other element as well. So 1, 2, for example, is an element of order 2 in my group. And so it had better be related to an element of order 2 in A5. But 1, 2, 3, the 3 cycle, does not have order 2, right? It has order 3. So 1, 2, 3 should probably be related, if it's related to anything here, it should be related to one of my elements of order 3 from S3. And then 1, 3, 2, likewise. Maybe we can just make that assignment here, right? And again, this would seem to pass muster because these are elements of order 3, and they're related to the elements of A5, these elements of A5 that have order 3, right? And then my identities are mapped to my identities, order 1, right? But then what about these transpositions, 1, 2, 1, 3, and 2, 3? What can I relate those to? Well, what are their orders as elements of S3? Their orders are 2. And because isomorphism preserves the order of elements, I'd better relate those to elements of order 2 inside of A5. So where do I find an element of order 2? Well, here's one, right? This product of 2 transpositions, 1, 2, 3, 4, that's an element of order 2. So I should relate 1, 2 to 1, 2 composed with 3, 4. Then what should I relate 1, 3 to? Some other element of order 2. 2, 3 should be related to some other element of order 2. But here's a bit of the problem that we face, is we don't just need to ensure that the orders correspond. We also need to know that for sure the entire, we need to know that the whole, how do I want to say this? We need to know that the homomorphism property, the product rule, is satisfied for every combination of elements that I could choose here. And so what I think what I want to do here, is I want to come up with a systematic way just to relate the elements of S3 to elements of A5. And so here's what I'm going to do. Here's my function that I'm going to define. I'm just going to say, let's let phi, whoops, other phi. Uh-oh, what did I just do? Oh boy, I just lost some of my work. So here's what I'm going to do. Given any element in S3, I'm going to make an element in A5 just by composing sigma with the transposition 4, 5. Right. So, for example, this would send 1, 2 to 1, 2, 4, 5. And if we think about that for a minute, 1, 2, 4, 5 is an even permutation of 5 symbols. Right? 1, 2 is an element of S3. This is even because it's a product of 2 transpositions. And then each of my 3 transpositions from S3, I can send to those. Right? And so that's what I'm going to do with my odd permutations. For my even permutations, I'm just going to keep them as they are. Right? So I'm going to take the identity and send it to the identity. I'm going to take my 3-cycle 1, 2, 3 and send it to the 3-cycle 1, 2, 3. And I'm going to take the 3-cycle 1, 3, 2 and send it to the 3-cycle 1, 3, 2. Right? And so this correspondence, it's easy to see that it preserves the orders of elements, order 2, order 2, order 1, order 1, order 3, order 3. Now the only question is, how do I know for sure whether or not this will satisfy the product rule? The only real question is going to be so obviously if I take any of these and multiply them with one another, that since these are just being left alone, this is just the identity function on these 3 permutations. And so the product rule will be satisfied because it's always satisfied for the identity function. It's always a homomorphism. So the question is, if I take something from this group and something from this coset over here, and I combine those together, will the product rule be satisfied there? So just as an example, I can check that this is true. That if I take 1, 2, 3 and 1, 3, then on the one hand, if I just simplify this out, how do I simplify this product of permutations? Well, this is a good opportunity to get back into those nuts and bolts. 1 goes to 3, which goes back to 1. So 1 stays put. 3 goes to 1, which goes to 2. So 3 goes to 2. And then 2 goes to 3. So this closes that cycle. 3, 2. It's the same thing as 2, 3. And then to check the homomorphism property on this, we'll note that 2, 3 is getting mapped to 2, 3, 4, 5 by this function. But meanwhile, 1, 2, 3 is getting mapped to 1, 2, 3. 1, 3 is getting mapped to 1, 3, 4, 5. And now 1, 2, 3 composed with 1, 3 is going to give me 2, 3 again. 2, 3, 4, 5. And so the product rule is satisfied, right? If I take the product first and then apply my function, I get the same thing as if I apply my function first and then combine the results, right? That's true when I choose one of these combined with one of these. It's also true if I take 2 of these odd permutations and compose them together, because when that happens, each of them is going to give me a factor of 4, 5, but those factors of 4, 5 are disjoint from these originals, and therefore we can rearrange them to be together. They cancel one another out. So just to let me show you the details on that real quick too. Right. That if I take 1, 2 composed with 2, 3, for example, then on the one hand, if I do that simplification, 1, 2 composed with 2, 3 is going to be the 3-cycle 1, 3, 2. No, 1, 2, 3. Right? 1's going to go to 2. 2 is going to go to 3, which stays put. And then 3 is going to go to 2, which goes to 1. So it closes up my 3-cycle. 1, 2, 3, meanwhile, under this homomorphism, is going to go to 1, 2, 3. But then 1, 2 is going to become 1, 2, 4, 5. 2, 3 is going to become 2, 3, 4, 5. But since the 4, 5 is disjoint with 1, 2 and with 2, 3, we can transpose these two, and I get 4, 5 composed with 4, 5, and that cancels. 4, 5 squared. And that's just going to give me 1, 2 composed with 2, 3, which is equal to 1, 2, 3. So that's the main idea. That's how we can set up a function. So phi of sigma is going to equal sigma, but then I'm going to compose this with n plus 1, n plus 2. Just the transposition. It transposes n plus 1 and n plus 2. And we're going to do that for the odd sigmas. And then we're just going to leave the even sigmas alone. And we can show that this function is, well, this function is definitely not going to be onto, right? Because not every one of the elements of A5 is accounted for in this list. After all, there's 60 elements in this group, but we're only ever going to be able to hit at most 6 of them from S3, right? Even when I replace this with n and n plus 2, the situation is even worse. N plus 2 factorial over 2 is going to be a lot bigger than n factorial, right? So there's no way we're going to be able to have an onto function. But as long as the function is 1-to-1, then we know for sure that the image of that function is going to be a subgroup of A5. Right? So all we really need to show is that this phi is 1-to-1 and also has the homomorphism property. So why is it 1-to-1? The homomorphism property we talked about down here. You can imagine what the generalization for that looks like. It's 1-to-1 because if phi of sigma equals phi of tau, then if sigma and tau are both even, then phi of sigma and phi of tau are just equal to sigma and tau, respectively. If both are even. If both are odd, then it would mean that sigma times this transposition, n plus 1, n plus 2, is going to be equal to tau, right? But sigma and tau are both originally elements from Sn, right? And so this thing on the right has to stabilize the n plus first and n plus second positions, and therefore sigma must also stabilize the n plus first and n plus second positions, and so sigma must have been equal to tau. Sigma equals tau, and this is if both are odd. Or no, I guess this is both. This is 1 even, 1 odd. So anyway, we end up with that argument there as well. So this is kind of a, this was a really challenging kind of problem for working with permutations, but hopefully it gave you a chance to just get your heads back into how you compute with permutations, how even permutations versus odd permutations work, how they compose together, and then also think a little bit more about isomorphism from this example, that it needs to be something which is 1-to-1 and onto if it's going to be isomorphic to the whole group, and then also needs to satisfy that homomorphism property. So that's where we're going to wrap up the live stream for tonight. The second exam is going to cover these 5 topics, and then the last remaining topics for the semester we'll have a take-home exam on that will cover cosets, Lagrange's theorem, and normal subgroups and factor groups, and that's where we'll end up for the semester. So I look forward to working more with you on those, and I will see you back in the classroom this week.